So this is going to be volumes of revolution, and just want to do a couple examples and really where it comes from as well. So what I want to do is I want to revolve the region bounded by y is equal to the square root of x is equal to 2, and y is equal to 0. And first we're going to revolve it around the x-axis. So if I look at this piece here, I know that the square root of x looks like this. And then we have x is equal to 2, which is right here. So this is x is equal to 2. This one was y was equal to root x. And then of course y is equal to 0, which is going to be the x-axis. So I want to revolve this region about the x-axis. So we're going to spin it around this way. So what we know is in order to find the volume is going to be calculated by the integral from a to b of some a of x dx, where a of x is the cross section. So this is the cross section. Really, it's the cross-sectional area is what we say. Now this comes down from this idea that if I want to find the integral of a function, so say f of x, if I want to integrate this, this region from say like a to b, if I want to integrate this, really what you have to do is you integrate the integral from a to b of just f of x dx. And the reason why this is the case is because if you look at the cross-sectional region, like if I slice this, this slice is essentially the height, and then this blue thing is going to be your dx, or really your width. So you're adding up all these slices. So that's why really this is f of x minus 0, which really comes down to the cross section. So in this case, f of x is our cross section. So now in this case, if we spin this thing around the x-axis, what we're going to build is some kind of half of a football essentially. So what I like to do is I like to come up with some kind of general cross section, and let's do it in pink because it shows up real nice. So what I'm going to do is I'm going to slice it right here. Now remember that we have to spin this thing around the x-axis, and when we do, it's going to generate something that looks like this. Now this is a three-dimensional disc, and its cross section really is this cross section of this disc. So this is now coming out of the board a little bit in 3 dimensions. That's why it looks like half of a football. So what I'm going to have to do is I'm going to have to sum up all these discs. So this is going to be the sum of all those discs. So in this case, a of x, let's write this I guess in here, which is going to be our cross-sectional area, is, well, this disc, the area of that disc is going to be pi r squared. So this is going to be equal to the integral, and we'll talk about the limits in a second here, of pi times, well, it's radius squared with respect to x. And the reason why this is respect to x because I'm adding all these in the x direction, so we're really sliding this way. So we can see that we're going to start at right here, which is going to be x is equal to 0 all the way to x is equal to 2. So this goes from 0 to 2. Now our radius is not really just this point here, but it's going to be all points on this curve. So as this thing slides to the curve, the radius is going to get small all the way to this big part. So really the radius is going to be the distance between this dot and this dot, which is going to be my function minus 0, kind of similar to that idea right there. So the radius is going to be the square root of x minus 0, which is just going to be the square root of x. So this would just be root x. So now when we're going to simplify, and then we're going to integrate. So this is going to be equal to the integral from 0 to 2 of pi times x dx, which is going to be pi x squared over 2 evaluated from 0 to 2. So then when we plug in 2 squared is 4 over 2. So this will be pi times 4 over 2. Sorry, 4 over 2, 2 squared over 2, minus pi times 0 squared over 2. So this is going to just be 4 over 2, which is going to be 2. So this will be equal to 2 pi. So what I want to do is I'm going to spin this thing around something that's not the x-axis, and we'll still spin in this direction and explain why we're going to go in the dx. So let me erase it. I'm just going to choose another axis of revolution. All right, so I set this up the same exact region. We're trying to find this bounded region right here. And now what I want to do is, instead of spinning this around the x-axis, what I want to do is I want to spin this around x is equal to -1. So this is going to be equal to x is equal to -1. So I'm still going to grab a cross-section of this. So this is going to be our cross-section. And now when I spin this around -1, we can see that this bottom point is going to produce this, and this top point right here is going to produce this other part of this disk. Now, we call this the washer method, which is nothing more than an extension of our disk method, because this looks more like a washer than a disk. So I'm going to be adding up all these washers. So it's going to kind of look like really kind of like a hollow football where the tip is going to be missing. So it still comes down to, for finding these revolutions, is the integral from A to B of the cross-sectional area. So this is going to be equal to the integral from A to B. Well, our cross-sectional area, we're going to have, when we have a washer, this is going to be pi times the big radius squared minus pi times the little radius squared d. Well, we can see that this washer is sliding in the x direction, so this is going to be dx. Now, this is nothing more than big disk minus little disk. That's all that represents there. So these radii are what we're going to have to pay attention to. So this is going to be equal to the integral, well, still from 0 to 2, the same summation, of pi times, now a lot of times we like to do the integral from A to B. We pull out the pi, and then we say this is r squared minus little r squared, dx. So that's the other formula, just pull it out the pi's. So finding the big radius and then squared. Well, the big radius is going to be the distance between, well, it's the radius of this circle. Let's do this in color. So it's going to be the radius of this big disk here, which means it's going to be this dot minus its center. So this is going to be root x minus this -1. So this is going to be equal to root x minus that -1 squared. So really that's just the distance from these two dots. So this minus this squared, which is going to be root x plus 1 squared. So let's simplify that. And then minus pi times, well, we have to find this disk here. So this disk, which is going to be this dot minus this dot. Now this dot was y is equal to 0, and this dot is still a negative, sorry, should be y equals -1. I'm sure you guys are screaming about that. So this would be y is equal to -1. So this is going to go from y is equal to 0, so this will be 0 minus this y, which is equal to -1. And this is going to be dx. And what we can really verify here is that this disk, as you slide through here, its radius is not going to change. So I can tell that its radius is 1 every single time. So simplifying this is going to be the integral from 0 to 2 of pi times, well, I'm going to square this binomial. So it's going to be root x times root x, which is going to be x. Outside and inside is going to give us 2 root x. And then last is going to be 1 times 1, which is 1. And then we got minus, pi dx. So in order to integrate these things, we can pull out the pi. This is going to be the integral from 0 to 2. Actually, let's integrate them while we're at it. So this is going to be pi, and the integral of x is going to be x squared over 2. This is the same thing as x to the 1/2. So this is going to be plus 2 times x to the 3/2 divided by 3/2, which means that's going to be 4/3, and then plus x, and this is going to be evaluated from 0 to 2. All right, so plugging these things in, this is going to be equal to pi, oh, did I miss this too? Minus 1. Oh, you got it? This is going to be x minus pi x. So this is going to be minus 1. Minus x as well, from 0 to 2. So those will cancel because this is pi minus pi. And simplifying this thing further, we're going to have x squared over 2 plus 4/3 x to the 3/2 evaluated from 0 to 2. Now, plugging in 0, they're going to be gone, so that'll all be 0. So I really only have to evaluate this at the top. So this is going to be 2 squared over 2, so that's just going to be 2, plus 4/3 times 2 to the 3/2. So simplifying this, this is going to be equal to pi times 2 plus, this is going to be the square root of 8. So 4 root 8 over 3. And if it bothers you, you can write that as 2 root 2. It does it. I'm good with that. Okay, so next. I'm going to pause this. We're going to rotate this way. All right, so same thing. We have y is equal to root x. We have x is equal to 2, y is equal to 0. But now we're going to rotate this around this axis here, so around the y-axis. So it's going to spin this way. Okay, so in order to do that, we know that we're going to have to slice this thing perpendicular to its axis, so our slice is going to look like this. So when I spin this around, this is going to look like another disk. But now what we know is we are adding the disks in the y direction. So when I set up the integral, my volume is going to be equal to the integral from a to b of, well, since this is a disk, we're going to have pi times capital R squared minus pi times little r squared. D, well, I'm adding in the y direction. So we're going to have to figure out what these are. So when you plug in, well, I can tell that it goes from 0, and then when you plug in 2, this is going to be root 2, so this is going to be root 2. So not very pretty, but this is going to be from 0 to root 2. I mean, that's because this point right here has the point 2 comma, f of 2 or 2 comma root 2. And now we have to take a look at the radii. So this is going to be equal to the integral from 0 to root 2 of pi times, now its big radius is going to be, remember that it's going to be the radius of this circle here, or this disk right here. So it's going to be big dot minus its little. So right minus left. When you're working with the y's, this was larger, this was smaller because you're moving in the positive direction. Now x as it goes this way, like these will give you bigger numbers, these will give you smaller numbers. So this is x is equal to 2, and this is x is equal to 0. So this is going to be equal to 2 minus 0, and this is going to be squared. Minus pi times the little radius is going to be the radius of this yellow one, so this one right here. So it's going to be this dot minus this dot. Now, we can tell that as I'm sliding up and down, this radius is not changing, but this radius will. So since it's connected to this curve here, now we have to be careful. This is all dy's. These need to be dy's. Now, for the previous one, when they were dx's, you had to solve the functions for y, so then the independent variable is x. Now, since we're sliding in the y direction, we're going to have to solve for x, which makes the independent variable y. So, solving this for x is going to be equal to y squared. So, this is going to be, this curve here is going to be y squared minus a 0. So this is y squared minus its center, which is going to be 0. And this is all squared. Okay, so now simplifying this, this is going to be the integral from 0 to root 2 of pi times 4. Let's write this as 4 pi. So 4 pi, that's what this is, 4 pi, minus pi times, well, y squared squared is going to be y to the 4th dy. And now this is easily integrable, so this is going to be 4 pi y minus pi times y to the 5th over 5 evaluated from 0 to root 2. So then we'll plug in the top, we'll plug in the bottom. So this is 4 pi root 2 minus pi times root 2 to the 5th all over 5 minus, well, when you plug in 0, this will be 0, this will be 0, so this will all be just be 0. Now, this is not really a very nice looking number here. So So we'll just leave it as is. If you wanted to simplify it, you could, just like the root 8 was 2 root 2, but this is, root 2, root 2, root 2, root 2, root 2. So, that will give you 2, that will give you 2. So I could write this as 4 root 2. So this is 4 pi root 2 minus pi times 4 root 2 all over 5. And then you could combine these things because they are of root 2's, but we're good with this. So next what I want to do is I want to rotate this off of axis as well. Let's go like over here. So I'll pause it and do one more. All right, so what I want to do is I want to spin this about, let's do x equals 2. We've done enough washers. So let's do it here, x is equal to 2. So when we make a slice, we're going to have to slice it perpendicular. So it's going to look like this. And then when we spin this around x equals 2, what we see is we're going to build a disk that's adding in the y direction. So this is going to be, our volume is going to be equal to the integral from a to b of pi r squared dy. We're going to add in the y directions. The reason why this is just pi r squared is because this is not a washer. This is just back to a disk because I chose x is equal to 2. There's no space. Now, again, this was y is equal to root x, so this still is going to be 2 root 2, so this will be 2 root 2, so this is from 0 to root 2. Now, I want to, I need to find the radius, so the radius is going to be, this right here. So we have to be careful when we do the radius, that the radius is going to be the distance of essentially that line right there. Now, the larger number being 2, the smaller number being on this curve. Now, this is x equals to 2, and just like this, since we're doing this in terms of y, I need y to be the independent variable, so I have to solve this for x. So this is going to be equal to, that's going to be equal to x squared, or y squared. So then this is going to be, 2 minus y squared for its radius. So this is going to be the integral from 0 to root 2 of pi times its radius, which is going to be equal to y squared. I lied. Remember I said bigger number minus smaller number. The bigger being this 2, the smaller being the y squared. So 2 minus y squared, all squared dy, because I still have to square that radius. So this is going to be equal to integral from 0 to root 2 of pi. When you square this, it's 2 times 2, which is 4. Outside's going to give you a negative 2y squared. And then inside's going to give you another negative 2y squared, which is minus 4y squared. And then negative y squared times negative y squared is plus y to the 4th dy. All right. So integrating this thing, this is going to be, the integral is going to be 4y minus 4y cubed over 3 plus y to the 5th over 5, evaluated from 0 to root 2. Now again, what's nice is the lower limits, all those are going to be 0, so all I have to do is plug in the upper limit. So this is pi times 4 root 2 minus 4 times root 2 squared, cubed, all over 3, plus root 2 to the 5th over 5, and then of course minus 0. And we can simplify this. This is, root 2, root 2, root 2, so this is going to be 2 root 2 times 2, which is going to be 8. So this would be pi times 4 root 2. Again, there's the product of 3 factors of root 2. So root 2 times root 2 is 2. Then I'll still have root 2, so 2 times 2 is 4, so minus 8 root 2 all over 3. And then similarly, we did this before. This is going to be 4 root 2, so plus 4 root 2 all over 5. And then you could add these things up just by adding their coefficients. Really, this is going to be pi. You could add 4 minus 8 thirds plus 4 fifths, root 2. And just for the heck of that, let me figure that out, which is going to be pi times 32 over 15 times root 2. So that really is kind of an example of how to find volumes of revolution using really the slicing, the disk, or the washer method. And, on axis, off axis, both adding in the x direction and also the y direction. I'll see you next week.